Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark, and we're now going to start talking about how to solve the Schrodinger equation, what that means, how it's done in practice. And we're going to start with some simple constructive techniques to give you a few tools that you can use if you're stuck in solving a quantum mechanics problem. Sometimes a few of these simple tricks will help you see your way through, help you identify appropriate scaling relations, and the like. So let's proceed. Okay, here's the Schrodinger equation, which you've heard a lot about already in the course. Psi is a wave function, h the Hamiltonian operator, IH bar d psi dt is h psi. And the precept of quantum mechanics is that all accessible information about the state is contained in the wave function. Now, this is for an isolated system. When we're talking about two interacting systems, or a system in a bath, and there's a lot more nuance. But let's just stick with simple many-body systems in the absence of noise or thermal bath, because that in itself is an interesting enough problem. So, in other words, if we know the wave function at a given time, we can just sequentially integrate this equation using some technique to find it at a later time. So, why in this era of high-performance computing and all these other wonderful things is anyone really worried about solving the Schrodinger equation? The inline quiz contains some sort of an exercise on thinking about how you use the Schrodinger equation to propagate the wave function forward in time. So, from a formal and even a practical perspective, for very simple systems, solutions to the Schrodinger equation are fairly straightforward to find. But in real life, we're encountered with problems that involve atoms like ytterbium, 70 electrons. This is a system I happen to have worked on myself with wonderful collaborators, Mariana Safronova, Sergei Porsev, during the past year, and it's motivated by determining the corrections to atomic transition frequency due to the presence of a thermal background for application in next generation atomic clocks. Well, a very simple consideration will show you that even a crude representation of the 70 electron wave function on a coarse grid would just be completely infeasible by today's and presumably just about any future technology that we know of. So physics-oriented approaches that take advantage of approximations, reasonable approximations, I think are always going to be essential. And so learning how to solve the simple systems gives one good guidance as to what you're going to have to do to deal with more complicated ones. Now, there are many cases in which one needs to solve the full time-dependent Schrodinger equation, let's say studying non-equilibrium quantum systems. Here's an example of solution of actually a nonlinear Schrodinger equation that describes a Bose-Einstein condensate. This is a spatial representation of density of an atomic cloud at various times, and so it's sometimes critical to have information like this. However, there's quite enough to be learned by understanding how to solve the stationary states of the system, which underpin a lot of the important phenomena that we see in nature. And so for the rest of this lecture is going to focus on the solution of stationary state problems. So here is the time-independent version of the Schrodinger equation. The Hamiltonian operating on psi is an eigenfunction of a Hamiltonian operator with eigenvalue E. And what does it mean to solve this equation? Well, the real-life problem that faces research physicists is they have some material system with an atomic and molecular composition, so they have a good idea of the Hamiltonian, but then they have particles moving subject to that Hamiltonian, and they need to find the eigenfunctions. Well, in other words, usually we know the form of interactions between the particles, and we want to find the energy and the wave function that describes a stationary state. We're going to get to that, but at first we're going to take a slightly different approach than is conventional, and that is look at some well-known function psi and see which Schrodinger equations they satisfy. Because if you have some experience doing that, then you can often make your way forward much more rapidly in solving a practical problem. This constructive approach that we're discussing now is actually extremely simple. Here's, for example, let's take a motion of a particle of mass m and a potential in 3 dimensions. Here's the Schrodinger equation for that, and by a trivial mathematical transformation, you can reduce it to this form. So in other words, if you know how to differentiate psi, you can find an energy and a potential for which it is a solution. So there's nothing better than solving a Schrodinger equation. Let's do it in the next inline example. So I hope you found that was a fairly easy problem to solve. It just involves taking a derivative. And now I might say that the solution is not entirely a contrived one. It's one that does occur in the theory of particle scattering. I mean, it's the basis for an important limit in the description of atomic collisions. Okay, so now back to this somewhat trivial procedure. You put in any function and it will solve a Schrodinger equation, but usually not an interesting one. But it's worthwhile looking at the cases where the interesting solutions are obtained. Furthermore, there are constraints on what are allowable solutions to Schrodinger equation. For example, in 3 dimensions, d cubed r psi star psi has got to be equal to 1 for a stationary state. The probability of the net probability of the particle being in the presence of the potential must always be unity, and so there are lots of choices of wave function here which cannot possibly be brought into this form. But let's go find some useful ones. Okay, so the last inline quiz simply has you take one of the most useful functions, not just in quantum mechanics, but in practical mathematical analysis of just about anything, and find out what type of Schrodinger equation it is a solution of. And that'll be it for this lecture. Then we'll go and apply that function in following lectures.